In this lesson, we're finally going to get to actual CPU and computer architecture using all the building blocks that we've developed over the last two lessons. So recall in lesson 6, we talked about memory. We had SR latches and D flip-flops, those let us store zeros and ones. And we had registers that were a set of many flip-flops to store a multi-bit number. Now, to just recall, in RAM, we have a bunch of registers, and each register has an address. Think about it like a neighborhood, and you have a bunch of mailboxes. Each mailbox can store some information, and each mailbox has an address, right? So maybe address 0 stores the number 10001010. So the question is, which of these addresses, what mailbox has inside of it the number 65? Well, you can go through and figure it out yourself. The answer is going to be address 3. That number in the binary number you see there is 65 in decimal. We also talked about arithmetic and how to do binary math. This is an example for addition. You can think through this yourself. Um, but the moral of talking about that is that the ALU, this thing inside the CPU, has all these various modules that can do addition and subtraction and all these other fancy operations that we might want. So we're going to take them for granted, but they are still just logical circuits, and I encourage you to go look into them yourself if you're interested. But the moral is we have the ALU, and the ALU can do math. But we still have some questions that remain, right? How does the CPU know what the ALU needs to do? How can the CPU know if it should tell the ALU to do addition or subtraction or XOR or whatever? And how does that, like, in terms of what physically happens with electricity and voltages and logic gates, actually tell the ALU to do that particular thing? How does the CPU know what address or memory to look at? How can the CPU read and write from memory? The CPU and RAM are separate units. How does this interface work? So these are the questions that we're going to get into today. To contextualize all of this, we need to understand the von Neumann architecture. So the von Neumann architecture is the fundamental common architecture for computers. The alternative is called the Harvard architecture. We're not going to talk about it. But the idea of the von Neumann architecture is that things in memory can mean numbers. They can mean data. For example, in our situation back on this slide where we had address 3 mean the number 65. But things in memory can also mean instructions, depending on whatever we're using it for at that given point in time. So that's what this point is here. We call those opcodes, operation codes, I think is what that abbreviates. I could be wrong, actually. So say my computer's doing some stuff and it reads 000 as an opcode in memory. It's just a RAM still storing the number 0, but because my CPU is deciding to treat that as an instruction, it's going to decode that into the instruction that it wants to perform. So in this case, it decodes 00 and 0 into addition. And in this example here, the red numbers, the first 3 bits are what the CPU will always treat as the opcode. And so the first one it'll do addition, then it'll do LDA, which is setting a value into memory, and then it'll do addition again. Don't worry about the specifics here. We'll get to those in a bit. But the main takeaway of this is that things in memory can mean instructions or they can mean data. There's no difference in how you store that information. The only difference is in how the CPU treats that information. So this was really important in terms of modularity of the design. Memory and the stuff outside the CPU no longer needs to think about how the CPU does the processing, right? It can be a central processing unit. That's what it stands for, right? Whereas RAM can just be memory of numbers as an abstract concept, not numbers that mean instructions versus numbers that mean data. It's just numbers. So yeah, that's one one. Now, we saw a bunch of weird things like CMP and LDA and MOV. What does that mean? Well, let's get into that by first discussing what the CPU actually does. What a CPU actually does is this core loop: fetch, decode, execute. You might have heard these buzzwords before. This is the core loop of what a CPU does as a state machine. So it's a machine that does this thing in this state as fetch, this thing in this state as decode, and this thing in this state as execute. Fetching is figuring out what it wants to do next from memory. So we noticed in this example here, we went from 0, address 1, address 2. Fetching is the process of after I'm done working on address 1, get the information from address 2 and store it. Then decoding is the process of taking, I've now stored these numbers 000100 in memory in my CPU register that we'll get to. Now decode that into the actions that I need to do and get set up for those actions. then execute is actually performing the actions that decode set us up to do. So to get a little more specific, we need three numbers to be stored inside the CPU to accomplish this task. Okay. There's PC, IR, and ACK. So what do those stand for? PC is the program counter. It stores the next RAM cell that we need to look at for an instruction. So I'm going to keep using this analogy of a mailman with the mailbox, a mailman going through a neighborhood. The mailman is doing some processing after it accesses each mailbox. So it might go to mailbox 0 and pick up this information. Okay. Then it's going to drive away and it's going to do some stuff on that information. But the mailbox has to know where he's driving to, or the mailman has to know where he's driving to. So the next mailbox that he's going to access is going to be this one. Okay. And he's storing the address 1 as the place to go for that next mailbox. Right. The program counter is telling the mailman, once you're done with the task that you're doing right now, go here for your next task. Okay. So if I'm within a processing loop, if I'm doing decode and execute, once I finish execute, I'm going to look at the program counter. I'm going to read that as a location in memory that I need to go to next. Okay. IR is the instruction registry. Remember what a registry is. A registry is just a set of numbers, a way to store a multi-bit binary number. Instruction is what the CPU fetched. So the program counter is the address that we need to go to fetch something. What we fetch from that address is going to be put into the instruction register. Okay? The instruction register is going to hold the number that we fetched from RAM. And then later we're going to decode the instruction register into the actual actions that we need to do. So in this case, we went and fetched this instruction 00000000 from memory. We'll identify the parts of that instruction later. But we just fetched this number that represents an instruction, and it's now stored in the instruction register. ACK is the accumulator, and we already talked about what that is. That's the thing that's wired to the input and output of the ALU, and it's what lets us do math, right? So we already covered what the ACK does and the purpose of it. The ACK is just the working number for the ALU. So those are the three things that exist as memory internal to the CPU. Now, to communicate between RAM and the CPU, we need buses, okay? We call these buses because the passengers are literally bits, right? They're buses that store people on them, and those people are bits. Okay. So the first bus is the address bus. That holds the address that we want to access from RAM. So imagine this mailman. He has a clipboard with a bunch of addresses that he needs to access, right? So on Google Maps right now, he punched in an address. The address that he punched in is what's going on the address bus. So once he gets to that location, he's either going to read or write something, right? That's something that he reads or write, that envelope that he's putting in the mailbox or taking from the mailbox, that's the data, right? And that goes on the data bus, okay? So the address bus is where to look. The data bus has what you look at, the actual information, the data. The control bus tells RAM, should I be writing what's in the data bus into the address that I'm looking at, or should I be reading from the address into the data bus? In other words, should I be dropping off mail or should I be picking up mail, right? So that's what the control bus does. And the control bus is still a binary label, but it's only a 1-bit signal. Either we are reading for a zero, that'll be a 0, or we're writing, that's a 1. So we usually just say read or write. We don't say 0 or 1 because it's only a 1-bit signal. But you might say 0 or 1. That's just what I put. Okay. Now, as a quick aside, I mentioned how we have an address, and that address somehow points us to just one location. But this is 1011. How do we turn 1011 into an actual location to go to? We do that, RAM does that. So this is outside of the CPU. This is in RAM, does that with a decoder. A decoder turns a binary number into a single thing that's on. So in this case, our input is 0110. That's the binary number 6, and output number 6 is on. If I change the input to, say, 1110, that's binary 14. Now output 14 is on. This is just a circuit of logic gates. It's actually a very simple circuit. It's a bunch of NOT gates and a bunch of AND gates. And it just activates exactly one output that corresponds to the decimal conversion of whatever our input in binary was. So in practice, this converts our address, which is stored as a binary number, into an activation of the memory register that we care about. Okay. So- And then yeah, there's also a multiplexer in RAM. But th my point of mentioning this is internal to RAM. All RAM wants is the address that you want to go to, a thing of data to either write or read to or from, and an instruction of whether it should write or whether it should read. Okay? That's all RAM wants to use. Once RAM has that, it can figure everything else out himself, and then we can go back to the CPU and do our operations there. So the decoder, I encourage you to look into that yourself. It's an important logical circuit, and it's fairly simple to kind of trace through the ones and zeros and identify for yourself what's going to be on, what's going to be off. So just to recap where we're at so far, let's regroup. I know I've presented a lot of vocab words. Inside the CPU, we have the PC, the IR, and the ACK. PC is the program counter. The program counter keeps track of where to go for the next instruction once we're done doing whatever we need to do on our current instruction. The IR is the instruction register. It stores our current instruction so that we know what we're trying to do right now. The ACK is the accumulator. That's what the ALU uses to do math. Remember that one input of the ALU and the output of the ALU is wired to ACK. To communicate with RAM from the CPU and vice versa, we have the address bus, the data bus, and the control bus. The address bus is where to look. It's what we punch into Google Maps. The data bus is what we are looking at. It's the mail that we pick up or drop off. And the control bus is whether we are reading or writing, whether we're picking up or dropping off. Okay. There's two other components within the CPU that aren't registers. There's the ALU. We talked about that last time. And now we understand what this wire from RAM to the ALU is. That's the data bus. That's the thing that we read from RAM. So we access some value from RAM that puts something on the data bus, and now the ALU can use that thing that's on the data bus to do math. So this wire is not every single register of RAM is connected to the ALU. We have to pick a value of data. We have to pick an address, get data from that address, and then only that data connects to the ALU. Because again, the only way that CPU and RAM can interact is through these three buses that we talked about, the address bus, the data bus, and the control bus. The other essential component is the control unit, and that's what we're going to take some time to work through now. The control unit is basically the boss of everything during the decode phase. Remember this fetch, decode, execute? The decode phase is handled by the control unit. Okay. Now we're going to black box over the digital logic gates, but fundamentally it is still just digital logic gates. There's no non-logic gate fanciness going on here. It's still just digital logic. Okay. And as an aside, when you design a computer, you use hardware description languages like Verilog or VHDL. Um, so like a professional computer designer, computer engineer might use these languages and actually design a chip by writing quote unquote code in these languages. It's not code because it's not something that you're executing on your computer, but it basically turns what you write into actual hardware, maybe on an FPGA, field programmable gate array, or some other uh, ASIC, whatever kind of system. Okay. So you literally write these things with logical operations in what feels like code when you're designing circuits. This is like CAD, but for digital circuits. So the control unit essentially maps a binary number from the instruction to an actual thing that it does. Remember, we read the instruction from a lookup table of opcodes. So we're now saying, okay, fine, I've gotten my opcode, but how do I turn that opcode into an actual thing for the CPU to do? The answer is we literally have a system exactly like this decoder. We take in the opcode as the input here, so opcode on the left, and then on the right, we have connections that go to turn on different parts of the CPU, right? So say, I'm going to get your output, or I'm going to get your output. The hardware always exists to do addition. The hardware always exists to do subtraction. We're not changing the hardware that exists. What we are changing is whether the hardware is activated to connect to an output. Okay, we're saying you are now connected to the output. Addition should go to the output. Or I'm saying subtraction should go to the output. We're literally changing what wires are allowed to, or sorry, I should say, uh, what connections are allowed to go to the output. It's hard to black box over this, but I guess you can take it on faith that we are not changing hardware. We're just changing what's on and what's off. So let's go through this. The control unit needs to map these binary numbers to some combination of the features that we have in our CPU that correspond to what we want to get done. So we'll get to this in a second, but in the final course challenge, I'm going to give you guys a CPU, and you have all these different instructions the CPU can execute, and you're going to be able to use those instructions to accomplish different tasks. So what we're asking is, what do each of these instructions mean for the control unit? What does the control unit need to do to decode this instruction during the decode phase of fetch, decode, execute? Well, we're going to fill these columns with ones and zeros. So a 1 in this ALU add column means that we're putting a 1 on a wire that activates addition. Okay? We are literally saying we're putting a 1 into an enable thing for addition circuitry that lets addition feed an output. Okay? The addition circuitry always exists. It's not that we're like adding it in whenever we need this to happen. All we're doing is allowing the addition circuitry to actually feed the output. Okay, I really want this to be clear. The control unit doesn't change hardware, it just changes what's on and what's off. Okay. The same logic applies for subtract. It puts a 1 on the wire to activate subtraction. If we want to write something into memory from the CPU, we need to put a 1 on the control bus's bit, right? Because 1 for the control bus means write, 0 for the control bus means read. Now, notice here, our add instructions are we add the first 4 bits in the cell's instruction. So say this cell right here. Let's make it an add instruction. So 0, 0, 1, 1. So the first 4 bits mean this instruction is saying to do addition. The second 4 bits say do addition with this memory address. So if I have an instruction like addition, then the last 4 bits matter. The last 4 bits are telling me I need to do addition, I need to do addition, and I need to do it with this thing from RAM. And so we need to write back into the address bus to access a new value of RAM. We already fetched the instruction, but now we need to fetch something else to actually execute that instruction. Okay? So that's what's going on here. So it puts a 1 on the wire that activates a connection between the instruction register and the address bus. In other words, it's going to write these last 4 bits into the bits of the address bus, which currently has nothing, but it's going to be these 4 bits over here. Okay. And the same thing applies for the program counter. If I want to overwrite the program counter, for example, if I'm doing a loop where I go cell 0, 1, 2, 3, and then go back to cell 0 to do some more things, then I need to overwrite the program counter's bits. And you're going to do that with the same sort of logic. Okay. And so I encourage you to fill in this table yourself. Just take a second and work through it. Okay. So for loading, we don't want to do addition or subtraction, obviously, and we don't want to do any writing. And we also don't want to do anything to the program counter. We're not doing any looping or jumping around. However, what does the load instruction mean? Let's go back to our tool here. Load means I want to write a value into the accumulator from memory. So our load instruction says, let's say we write a load into cell 1, 0, 0, 0, 1, 1, 1, 0, 0. This says the first 4 bits mean load, the second 4 bits mean load the thing from address 12. And because I need to then get the value from address 12 during execution, I need to write that address onto the address bus. So that's why we have to use it. We have to say address bus. You need to use whatever's in the instruction register right now. So for storing, let's think about this in the same way. The store instruction is store a value at this memory address. That's what A is, the particular address. So that means I need to write into the address bus because I need to access a certain address. But because I'm storing, that means I'm writing a value into memory. So I also need this control bus's bit to be 1. So add and subtract are going to be 0. Program counter is going to be 0, but these 2 columns are going to be 1. For addition, well, the addition instruction is we need to add a value to the accumulator, so addition needs to be turned on. And when the value that we add is going to be a value from memory. So we need to write the address of the thing that we want to add into memory to be able to, sorry, let me say that again. We need to write the value, my God. We need to write the address of the thing that we want to access into the address bus so that we can add that thing to the value of interest. In other words, we need to write A into the address bus so that we can get memory values at the address A and add it into the accumulator. So that means we need to use the address bus and we need to use the addition feature, but we don't need to do any writing into memory. We don't need to do subtraction and we don't need to overwrite the program counter. Okay, done. Now, what about subtraction? Well, same logic. We do need to access memory to figure out what value we're going to subtract. And we do need to do subtraction, but everything else is zero. Now, what about jump? Well, jump means my program counter starts at 0, then goes to 1, then goes to cell 2, then goes to cell 3. But maybe I get to cell 3 and I want to do a loop. Maybe I'm doing multiplication, where multiplication involves, and this is kind of a hint for the course challenge, addition many, many times. Well, then I need to loop and I want to go back to cell 0 and repeat the actions. Well, that's going to be done with this jump command. And it says jump to cell A. A is a program counter thing, right? Remember how the fetch, decode, execute loop works. We fetch an instruction, we decode the instruction, we execute the instruction. After executing the instruction, we go fetch our next instruction. But if we just lie to the CPU and say, you've gotten to cell 3, but your next instruction isn't going to be cell 4. Your next instruction is going to be back at cell 0. All we need to do is overwrite the program counter and tell it that the next instruction will be at cell 0. So what that's going to manifest as, we don't need to do addition or subtraction, and we don't need to write anything into memory, and we don't need to write anything into memory, but we do need to overwrite the program counter. In particular, we need to overwrite the program counter with whatever address we're saying the next instruction will be at. In other words, where we need to jump to in memory. And so that last column is going to be a 1. And the same thing is going to apply for jump Z. Jump Z is jump conditionally. Do a jump only if a particular condition, in this case, accumulator equals 0, is met. So jump Z is a special one. It'll do the jump and it'll only overwrite the program counter if a condition is met. Okay, so before we get to the demo, and let's just fully restate this loop. Fetch gets the address that the program counter indicates the next instruction is at, okay? So that could be just the next cell, or if I'm doing a jump or a jump Z, it could be a previous cell. I could be doing a loop. It's just wherever the next instruction is located. It's whatever the mailman is entering into Google Maps for the next location to get an instruction. During fetch, we write the address into the address bus that we need to go to. We go to that address, you get the data from that address, and then write that data into the instruction register. During decode, you look at the instruction register and say, and the control unit says, okay, this means I need to do addition, and I need to do addition of this value from memory. Or maybe it says, I need to do subtraction of this value from memory. Or maybe it says, I need to go write this value into RAM. So whatever it does, control unit is going to take the instruction register and set up the things that need to be turned on or off to let those things happen. Then at execution, everything updates. All the clocks tick. Remember that registers update whenever a clock ticks? And so the control unit turns on a bunch of wires, and then execute ticks the clocks so that the new connections update the values in all of our flip-flops, whether that be in RAM or whether that be inside the registries of the CPU. So let's look at a demo of this. So what we're looking at here is a sample of adding 3 numbers. Notice at the bottom of my screen, we're adding 3 numbers. Okay. Our 3 numbers are set up in cell 10, cell 11, and cell 12. So I'll write the numbers. The number in cell 11 is 1 plus 4. That's 5. The number in cell 10 is 5. Cell 11 is going to be the number 7, and cell 12 is going to be the number 3. So we're trying to add 5, 7, and 3. And we need to put that output somewhere. Our program counter starts at 0. So when I press step, the program counter writes itself into the address bus. Okay? And the control bit is set to read. Sorry, the control bus is set to read. So we're going to read whatever the value is here, and that value is going to go get dumped into the data bus so that the data bus can then dump it into the instruction register. So just to reiterate, on the first step, the program counter wrote its address into the address bus. The address bus said, okay, let's go to this address right here, address 0. This address is then going to write its value into the data bus, and the data bus is going to write its value into the instruction register. So if I step, notice that's exactly what happens. Okay. Then next, we've now read the value. We're going to move into the decode phase. So our control unit is going to move to the decode phase and figure out what does this instruction mean here. Well, 0011 is addition. We're saying add into the accumulator a value from the memory address A. Well, that means I need to activate the program counter. Sorry, I need to activate the circuitry that connects the instruction register to the address bus. So I'll do this in a different color. We're going to have these 4 bits get written into the address bus. We're going to have these 4 bits activate addition from the ALU. And the address bus is going to go to the address that we want to access. In this case, it's going to be 1010, which is address 10. It's going to go here. It's going to write that value into the data bus. The data bus is then going to go into the ALU and then update the accumulator. If I step it, the CPU, the control unit is now in decode. So notice the description up here. We read the instruction register and we're in add, and we read that we have an address that we need to write into the address bus. By step, the address bus gets written with the value. Now the data bus is going to be written with whatever the value is from this address. And at the exact moment that the data bus has that value, now that's feeding the ALU, and so the accumulator gets updated. Notice that it went from 0 to our added value. Then, now that we've finished executing, we need to do the next fetch. So the program counter says the next fetch is going to be 0001. So we go fetch, and then we do this instruction. We need to load the value 12. I think I had messed with the instructions here, so I'm going to need to change this. But if this was the instruction, we would load the value 12, and so on. So you should play with this toy yourself and get a feel for how it works. But just to go through again what it does for this addition example. We first fetch. So we write the address that we want to access onto the address bus. Then the data gets written onto the data bus and into the instruction register. The instruction register gets decoded and the control unit sets up the ability to then go access the right address. So we write that into the address bus. The address bus points us to the right data cell. The data cell writes its value into the as one of the inputs to the ALU, which then updates the accumulator. Then we move to the next fetch, and we continue. Fetch, decode, execute, and then fetch again, decode, and then execute. And we keep going until eventually, notice what we've gotten here. Again, we had 5, 7, and 3 as our inputs. So our expected output was 10, well, was 15, and that is indeed what we got there. Okay, there's 2 other examples here. Strongly encourage you to go through this yourself. Multiplication by adding and addition of three numbers. It's a helpful thing to work through. But yeah, that's how a CPU works. So this is essentially the tool that you're going to use this on Friday. Uh, you're gonna do a check, and you'll get. Let me use the real tool. Actually, I think that'll probably be more illustrative. So I'll give you this one for free. This is an easy one, and I'll do it during the lesson as well. You're given the task that cell 15 holds a number. You need to write that number to cell 14. And I'm telling you up front, the fewest number of instructions you need to do this task is 2. It's pretty obvious what those instructions are, hopefully. We need to load the value from cell 15, and then we need to store that value in cell 14. So first in cell 0, we need to load cell 15. So load is going to be 0001. So that's going to, if I'm writing in here, 0001. And the next 4 bits are where we are loading from. We're loading from cell 15. 15 in binary is 1111. 1111. So we're loading cell 15. Okay. The next instruction is to store in cell 14. So store is 0010. And 14 in binary is 1110. So now if I run check, I got it correct. And this tool is going to give me a verify code. You're going to put this code into a Google form, and then you'll be good to go. And so we're going to score just by the number of verification codes that you're able to get. You'll notice these get progressively more difficult over time. These first 4 are pretty simple, hopefully. Tripling is also pretty simple, but multiplication, division, and squaring get quite challenging. So I think those will be really interesting if you're able to get the par solution on those. So good luck. I think it'll be a lot of fun. But yeah, that's all I got. Thank you.